Hello, it's Dumplet here. Here's an item on evaluation. Evaluate the following series. 1 squared over 5 plus 2 squared over 25 plus 3 squared over 125 and so on and so forth. As usual, pause this video if you'd like to give this item a try. But if you're done, let us dive into the solution. Alright, whenever we're given a series, we tend to take a look at the general term or like a formula or like a nice pattern to this sum, and we can kind of make the observation that I think the numerators are just perfect squares, so 1 squared, 2 squared, 3 squared, and so on. The denominators are just powers of 5, so 5 raised to 1, 5 raised to 2, 5 raised to 3, and so on. So generally it's going to be of this format. So the reason why we kind of wanted the format is for us to be able to kind of get the pattern. Now, here we have like almost a geometric sum. If the numerators are just of the same value, let's just say they're all 1s, then we can easily get the sum via the formula for the infinite geometric sequence, the a over 1 minus r. And practically speaking, that's the only feasible formula for us to use. Any other formula might be out of reach for now. I mean, yes, there might be a very nice formula to do this one, but let's try to solve this one using the infinite geometric series. Now, as with a lot of the questions where you're given with an infinite sum, maybe an infinite fraction, maybe nested radicals, or something similar to that, generally we make the nice substitution that s equals whatever the sum, and then maybe we're going to end up with something, or like maybe we can find a part of this sum that contains s, or maybe we can get something to simplify or something like that. But there is a standard procedure to solve these types of questions, and it is the following. Now, here we have s, and then generally speaking, we're going to take advantage of the n squared. Now, what do I mean by taking the advantage of n squared? Because the numerators are perfect squares, so we can kind of say that the numerators tend to grow quadratically in a quadratic with a degree of 2. So we're going to take note of the second differences, because if we recall from our lessons in algebra, if we take the second differences of the data points in a quadratic function, you're going to realize that it is going to be constant. So as with linear functions, the first difference is constant. For quadratic functions, the second difference is constant. So we're going to take this fact on the fact that on the n squared and the second differences. To use this fact, though, we have to do the following. So here from s, I got 5s. So I multiplied both sides by 5, and 5 is the like the common ratio of the denominators. That's why I'm using 5. So if the 5s here were 4, then I would get 4s. If this was a 7, I would use 7s. But in this case, I'm going to use 5s. And I'm going to take the difference 5s minus s, and I would be able to get 4s. And here's the thing that I have to do, because I want to take like the difference. I'm going to take the difference as indicated by the arrows. And this is very intentional, so we can take note of the, in this case, the first difference. So if the 1 squared becomes the 1 squared, and then the rest of the terms I'm going to follow the red arrows. So 2 squared divided by 2 squared over 5 raised to 1 minus 1 squared over 5 raised to 1. That's going to give me 2 squared minus 1 squared, so that's going to be 3 over 5 raised to 1. Now I'm not gonna simplify some of the stuff here. That's very intentional, so we can kind of see the pattern. Right, next term, the 3 squared over 5 squared minus 2 squared over 5 squared. That's going to give me 5 over 5 squared. 4 squared over 5 cubed minus 3 squared over 5 cubed. That's going to give me the 7 over 5 cubed, and so on. Again, this term is technically not given, but since we have a nice pattern going on, that's why we kind of wanted to get the formula so we could kind of know what will be the next terms of the sequence. Anyways, this will be the value of 4s. And if we kind of take a look at the numerators now, technically this is 1 over 5 raised to 0. If I take a look at the numerators, 1, 3, 5, 7, and I'm assuming if we follow the pattern, it's going to be 9, 11, 13, and so on. It aligns with the fact that taking the first difference of a quadratic, the data points in a quadratic function, you're going to get a linear relationship. So 1, 3, 5, 7, that's not a coincidence. It is just something that we intentionally did. So now that we have the 4s equals 1, plus 3 over 5 raised to 1, plus 5 over 5 squared, plus 7 over 5 cubed, and so on, we're going to do the same technique again. We're going to take another difference. So now technically it's the numerators are growing linearly, and we're going to take the differences, so it's going to be a constant. So in effect, the second differences of the original quadratic function in the numerators. All right, same thing. We're going to multiply by 5. So the 4s becomes 20s, and I'm going to do the operation 20s minus 4s, giving me 16s. And I'm going to still offset by 1, taking these kind of like diagonal differences. The 5 here becomes a 5. 3 minus 1, that gives me a 2. 5 over 5 raised to 1 minus 3 over 5 raised to 1. That's going to give me 2 over 5 raised to 1. And then you can kind of see that we're just going to do the other things similarly. All right. Now, upon taking another difference, we can kind of see a nice observation in the this part of the sum. Now, that part is already a simple infinite geometric series. As you can see, the numerators are all constant, so the second difference becomes like constant. So they're just all 2's in this case. And then we can easily use the fact that we have the nice formula for it. So a, which is 2, divided by 1 minus the common ratio, which is going to be 1/5. And this is going to give us 2 over 4/5. And that's going to give us 5/2 for the sum of the red highlighted terms. All right, so the red highlighted terms is going to be equal to 5/2. So 5 plus 5/2 is going to be 15 over 2. So 16s is 15 over 2. Solving for s, we're going to get s is equal to 15 over 32. And this will be our final answer. Hopefully you guys learned something new from this video, and I'll see you in the next one. Bye-bye!